Hello, this is Mr. White, and this video is on basic differentiation rules. There will be 3 exercises in this video, and in the first one, we'll use a graph to estimate the slope of the tangent line at several different points, and then we will find the slopes analytically. In the second exercise, we'll find the derivative of this function using our basic differentiation rules. And in the third exercise, we'll find the derivative of this function and remind ourselves that algebra really can be our best friend in the differentiation process. So back to the first exercise. We are asked to use this graph to estimate the slope of the tangent line to the curve y equals x to the negative 2/3 at the point shown and to verify our answers analytically. And we're provided the picture here. I'll remind you that using our pre-calculus skills, the shape of this curve shouldn't be totally surprising. Even if we weren't provided the picture, we should be able to look at this equation and say, hey, I can tell there's going to be a vertical asymptote at x equals 0. So that shouldn't surprise us. We should be able to tell that due to the fact that this is an even number here, that's x to the 2/3 power in the denominator, that's going to make sure that all our outputs are going to be positive. So it shouldn't surprise us that this graph is completely above the x-axis. So again, even when you're provided a picture, don't turn off your brain. Make sense out of it. But our task here is to use the graphs to estimate the slopes of the tangent lines. And we see 3 different given points to us, and we're given their x values. And they may look like some odd choices in x values at first, but we'll find out that they're those values for a reason. And we should be able to right off the bat envision what the tangent line is going to look like at each of those points. I should be able to look at point A there and envision a tangent line going something like that. And for point B, a tangent line something like that. And for point C. And I should already be starting to anticipate which of those are going to have positive derivatives and which are going to have negative derivatives. And are they going to be relatively large or small values? Brain should already kick into gear with those kinds of questions. Let's go through them one by one. Let's start with point A. And in point A, I've just gone ahead and put the tangent line in there. And let's estimate what the slope is going to be. Well, we see point A itself is on a grid point. In other words, it's at an intersection. It has integer values for its x and y. And I'm looking for another convenient grid point. And it looks like this is another one that will allow us to very conveniently and easily calculate the slope. Now, the way I tend to calculate slope may be a little different than some other math teachers. I tend to just look at the positive rise and positive run and then ask myself, overall, is the slope positive or negative? So if I'm contradicting what you've been told in the past, you'll see we end up with the same answer. So here's what I'm referring to. I would say the rise looks like 2 units, and the run would be 3 units visually, and overall the graph is going downhill, so that's what tells me that the slope is going to be negative. That's what tells me that I'm expecting a slope of negative 2/3. Now, one of my peeves with students is when students just write an answer there and don't tell me what they've just provided me. What is negative 2/3? We're saying that that's what we expect the slope of the tangent line at x equals 1 is, right? So say that. Say that that's what we expect that the derivative f prime at an x value of 1 is. And since we're just estimating here, we don't know for sure if it's exactly negative 2/3. I'll use the squiggly equal sign. But definitely make it a habit to say what it is you're writing down on your paper. All right, let's look at the second point. Again, at this point, we're just estimating, visually estimating our tangent slopes. And this one, we definitely have a negative slope still, but it's a lot more shallow. And at an x value of 27/8, that's not at a grid point itself, but we'll make do. So I'll shrink this a little bit. Now I'll ask, where are 2? I don't have to use this point itself in calculating the slope. So I'm just going to look for 2 other convenient points, and it looks to me like this is roughly a grid point. It may not pass exactly through negative 3, 1, but it's close enough for estimating purposes. Likewise, kind of over here. I'll say it goes through 8, 0. Now, whether you're looking at it and wondering, is it 8, 0, is it 9, 0, somewhere in between, we're just estimating. So let's just say 8, 0. And in this case, the rise is 1, and the run is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 1 over 11, but it's downhill, it's negative. So I'm claiming that f prime of 27/8 is approximately equal to negative 1/11. For the last one, x equals negative 1/8. We have a very steep positive curve, an uphill curve. And again, there aren't some nice, convenient grid points to use, so we'll just have to be permissive in our use of points to find the slope for. Looks to me like it goes through the point roughly 0, 7. And I don't see another convenient actual grid point, but I'll go ahead and choose this point. And I'm going to argue that it looks to me like that's about 1/3 of a unit to the left of the origin. So if this distance here is 1, I'm saying that looks to me to be about 1/3 of the distance there. So that would mean our slope is, our rise is 7 units up and down, right? And the run looks to be about 1/3 of a unit. And what's 7 divided by 1/3? Well, isn't that the same as 7 times 3? So I'm saying 21 is my estimate. 7 divided by 1/3 is the same as 7 times 3. And I am saying that that is my estimate for f prime of negative 1/8. Okay, so we've got our estimates there. Let's go back now and analytically see if we can come up with answers that roughly agree with our estimates. We're not expecting perfect agreement, but just that makes sense. We've been using the limit definition to find derivatives for a while, and again, I can't say it enough, that is something that we cannot ignore, and even as we learn some new tricks like the power rule, we're going to come back to the limit definition every time we need to expand our skill set over the coming weeks. Let me go ahead and acknowledge, though, that the limit definition is tough to use for this particular function. The presence of that fraction, that particular fraction up there, makes it rather tough to use. So let me show you what it looks like if we use the limit definition. And of course, I wouldn't discourage you if you wanted to just challenge yourself on your own. But I will say there's a little bit of algebra in here that I wouldn't expect the average student to get. So take that as a challenge, if you will. This is what the limit process would look like for that function. And it goes on, and finally I get an answer. So it's rather ugly there, and this is where we really become thankful that we are learning some new tricks like the power rule. So let's go back to this function, x or y equals x to the negative 2/3. And you may have seen in the limit process I was calling this f of x. And I was doing that earlier in the estimates as well. Again, we can use those rather interchangeably for this case. So whether we call this f prime or whether I call it y prime, I'm not going to be too super picky, but the power rule tells us that we could take that negative 2/3 and bring it in front, write the x, and then I can take the exponent and reduce it by 1. So I can go negative 2/3 minus 1, or I can think of it as negative 2/3 minus 3/3. Negative 2/3 minus 3/3 would give us negative 5/3. That is my derivative, whether I call it y prime, dy over dx, or f prime of x. They all mean the same thing, derivative. And that's the same answer that we got for that I got with the limiting process, but boy, was it a lot quicker with the power rule, huh? Okay, let's see what that gives us for our estimates now. Or I guess I should say, let's see if that agrees with our estimates. Let's scroll down here a little bit, and let's look at that first one. If y prime equals negative 2/3 x to the negative 5/3, analytically, that would tell us that, and I'm going to go back to the f notation here. That would tell us that f prime, when I plug in an x value of 1, because that's what we are given, f prime of 1 would equal negative 2/3 times 1 to the negative 5/3, which does simply equal negative 2/3. So that agreed with our estimate exactly. We were spot on with our estimate. There's our analytic answer, our exact answer, and here was our estimate, which agreed with it. Let's scroll down a little further. All right, here's the second point, and in this case, x was 27/8. So let's say f prime of 27/8 And this is where I'm going to give a big plug for mental math. Move this down a little bit. Of course, I could whip out a calculator here, but sometimes it's quicker to use mental math, and sometimes you're not even allowed to use a calculator. So if I write 27/8 to -5/3, I'm going to write some of this out. But again, I encourage you that for a calculation like this, practice doing this mentally. Think of this. Notice that 27/8, very conveniently, the numerator and denominator are both perfect cubes. The top is 3 cubed, the bottom is 2 cubed, and that's not a coincidence here. That's because if I take 27/8 and then I take the cube root, which is what that 3 in the denominator of the exponent tells me to do, that's taking the cube root of 27/8. So right now, 27/8 to the 1/3 power is 3/2. And then I'm going to raise that to the 5 power. So 3/2 to the 5 power, that's 3 to the 5th over 2 to the 5th. That's going to give me 243 over 32. It's kind of convenient to know your perfect powers pretty well. 243 over 32. The negative is going to flip that. That's going to make it 32 over 243. So again, I'm doing a lot of this mentally. And there's often times where I discourage students from doing too much mentally. I want you to show work, but for arithmetic like this, sure, do it mentally. And I'm sure we can have plenty more discussion in class about when it's appropriate to do things on paper versus when we should just do it in our heads. Anyway, multiply the result by the -2/3, and that's going to give me -64 over 3 times 243 is 729. And that is precisely f prime of 27/8. And let's see if our calculator can verify that. So even though I'm making a plug for mental math, I would like to see, do these two answers roughly agree? When we were just visually estimating, I had -1/11, and that's about -0.09. And here, analytically, we're getting -64 divided by 729. And not too far off, also roughly -0.09. So I'd say yes, this seems like a logical final answer for that slope at that point. Let's look at the last one there, and one more time, drag this analytic answer, this analytic derivative down. We said f prime of -1/8 equals roughly 21. Again, I'll invite you to pause at this point and see if you can mentally work out what that analytic answer here is going to give us. Let me go ahead and check it myself. I'm saying that f prime of -1/8 is going to equal, analytically, -2/3 times -1/8 to the -5/3. And same idea. This is a perfect cube of -1/2. So if I take the cube root, I'll get -1/2. Raise that to the 5th power, I'm going to get -1 over 32. And then that negative is going to flip it and make this just -32. Times -2/3 is going to give me 64 over 3. And that is definitely multiplication there. So that's what I'm claiming f prime of -1/8 exactly equals. I know 63 over 3 would give me 21 exactly. So 64 over 3 is not too far off. Using our mental math to say, you know what, I don't even need a calculator. I'm going to go ahead and say that's pretty good agreement with my estimate. All right, so it's always good to have an estimate so that when you look at your final answer, you go, yes, I think that makes sense, and I can move on. All right, find the derivative of this function. So let's use our basic differentiation rules. We can start weaning ourselves, for the moment, off of the limit process until we find we need more tricks. And let's think of the rules we've learned thus far. The power rule, the constant multiple rule, the sum and difference rules. Let's go ahead and apply those. The power rule says that if I were to differentiate just that x to the 4th, that I would get 4x to the 3rd. And since I am differentiating, this is where I want to make it absolutely clear that that's what I'm doing in this step. So I write f prime of x equals x squared. If I differentiate that with the power rule, that would give me 2x. And this one, it says cube root of x, but let's conceptualize that as x to the 1/3 power. And then when I apply the power rule, I'm going to get 1/3 x to the negative 2/3. I'm subtracting 1 from the exponent. So that was just the power rule. The constant multiple rule is the one that says that if I'm taking that power and if I'm multiplying it by just a constant, a 5, a -1, a 6, then I can just bring that down in the derivative line. So I can just bring down a 5 and multiply it by the derivative. And I can bring down a -1 here for the second one. And I can bring down a 6 here for the third term. So again, if this were something other than a constant, so for example, if this were sine of x, then we could not simply bring that down because sine of x is not a constant. So be careful. You can only bring down constants or treat constants in that manner. All right, and the sum and difference rule is what simply says that I can, if I have a function that equals this plus this plus this, I can simply add and subtract their derivatives accordingly. So this is 5 times 4x cubed minus 2x plus 6 times 1/3 x to the negative 2/3. And of course, I'll simplify that a little bit and end up with f prime of x equals 20x cubed minus 2x plus 6 times 1/3 gives me 2. X to the negative 2/3, that's the same as an x to the positive 2/3 in the denominator. And that's my final answer. Now, is there a way to check that on the calculator? There is. Our calculator is not going to directly give us derivatives, but if I think I know what the derivative is, I can type the original function in there as y1. I can type the derivative, what I believe the derivative is, as y2. And when I graph those, notice that the original function I have is bold. So if I go back to here, notice that I've got it such that y1 will be displayed in bold. And so the original function is the bold, the derivative is the non-bold curve, and let's just test a couple values there. I'm going to go to second calc, and I'm going to press the number 6 on my keypad, do derivative. And notice up there that I am working with y1. So I'm going to pick just some arbitrary point. I'm going to say 1, just because it's an easy number to type in. And I find that the derivative, the slope of the tangent line of that bold curve is 20. Well, that should be the y value of my derivative curve, right? So let me hit the up arrow button. Notice that now I'm on y2. The calculator is focusing on y2. And notice that indeed its y value is 20. So those two are in agreement with each other. Let's try one more point just to get a little extra assurance. Second calc dy over dx, number 6. Let's try the derivative at 2. The slope of the bold curve is about 157 and change. It's not even so I can't even really see it on the screen, but that's okay. It displays that the slope is about 157. And if I jump to the y2 curve, the derivative curve, I see that the y value is 157 and change. So this seems pretty assuring that I've got the correct derivative. Let's go to y3 here, or to the third exercise, complete the table. Here's our original function, and later on we're going to learn some more rules that tell us how to deal with functions within functions. That's going to be called the chain rule, and when you have one function over another function, we're going to learn the quotient rule. And at that point, students often jump into those fancy new rules, which sometimes are necessary, but in a case like this, it's not necessary to get all that complicated. A lot of times just doing a little bit of algebra up front will make your differentiation a lot easier. So let's not differentiate right off the bat, let's simplify. Let's say that this equals 10 times x to the 1/2. Our rational exponents, our fraction exponents, are going to make our job a little easier than radical signs. And 5x to the third, since that is in parentheses, not only is the x being cubed, but the 5 is being cubed. So I get 125 x to the third power. And I'm not even done rewriting it. Let's simplify that a little further. 10 over 125. If I divide the numerator and the denominator by 5, I'm going to get 2 over 25. And if I do my exponential rules, x to the 1/2 over x to the third is going to give me x to the negative 2.5, or negative 5/2. So I'm just doing my 1/2 minus 3 to get that negative 5/2. All right, again, I haven't even done any calculus yet. That was just algebra. So now I'm going to differentiate. Now I'm going to apply my power rule and make it absolutely clear that now I'm doing y prime. And I'm going to say that that equals 2/25 constant multiple times the derivative of this expression of x. So times negative 5/2 x to the negative 7/2. I just applied the power rule there. All right, that's going to simplify. So for my final step, simplifying, see, a 2 and a 2 cancel each other. A 5 up here cancels out one of the 5s here, so I'll get negative 1/5. And then an x to the negative 7/2, that's the same as an x to the positive 7/2 in the denominator. There's my final answer. If I want to check by calculator, I type the original function as y1. I type the derivative as y2. I'll go to graph here, and let's go to second calc number 6. Let's find the derivative of the original function. Let's say at x equals 1. And I'm getting negative 0.2, or negative 1/5. And if I jump to y2, I see that its y value is negative 0.2. Same deal, right? Let's do one more. Second calc 6 at x equals 2. And I see the slope is negative 0.018 approximately. If I jump to the y2 curve, I get the same number as the y value there. So consider it verified.